Munson 2104 asks for the force exerted by the water on this underwater gate. This gate is 2 feet down from where this axis y prime would meet the surface of the water, and the gate is 4 feet tall. Now this is in British units or US units, feet and inches and so on. Will work out way better if we convert this to metric to solve our problem. So 2 feet is about 0.6 meters, 4 feet 1.2, 6 feet 1.829. So we've got those conversions done for us. The question tells us that y prime is equal to 4x prime squared, describes the shape of the gate if we're in feet. So this is a gate that gets to be 2 feet wide up at the top and has a parabolic shape. So starting it down here at y prime equal to 0, it gets wider, but not as fast as it goes up. So if that's the shape of the gate in feet, then if we want to express y prime and x prime in meters, then y prime in feet is y prime in meters divided by 0.3048. X prime in feet, x prime in feet is x prime in meters divided by 0.3048. So substituting that into the equation, we can get an equation for y prime and x prime's relationship using units of meters. And this winds up being y prime equal to 13.12 times x prime squared. Or, reversing the equation, we can get the positive result, positive root of the equation, x prime, that's the one over here on the positive x side. The negative one will be exactly the same except in the opposite direction. This way, or noting that the width is twice the value of x prime, i.e. it goes this way and that way, then 2x prime, that'll be 0.5521 times the square root of y prime. So if we want to get the force, we're going to have to integrate over this area. The pressure integrated over the area. So the force will be equal to the integral over the area, probably should call out a double integral, of pressure and area. But if we're smart, we can observe that at a given height up here, the pressure will be the same all the way across. So we can take the same pressure all the way across that stripe and not have to integrate the second dimension. So that'll then become an integral from y prime equal to 0 up to y prime equal to 0 up to 4 feet, that's 1.219 meters, 219 meters of the pressure, which is going to be a function of y prime only, times dA, well that'll be dy prime, the small distance in that direction, times the width, w, which is also a function of y prime. So we need to sort out both of those, p of y prime and w of y prime, in order to substitute in. We've already got w of y prime up here, so let's get p of y prime. P of y prime equal to 0 is under the water by 6 feet, but that's at an angle. And it says that that angle is 30 degrees. So if that's 30 degrees, then we're interested in, to get this distance down here, that's going to be the sine of 30 degrees. So P naught will be equal to the distance down the ramp here. So that's 6 feet, or 1.829 meters. But we'll take the sine because we're only interested in the vertical distance, times the sine of 30 degrees. That's the distance under the water times rho g, or rho g times 1.829 times 30 degrees. The sine of 30 degrees is a half, so that'll be 0.9145. If it's water with a density of 998 times 9.81 times 0.9145, 9.81 times 998, that'll give us a pressure of 8953 newtons per square meter, or pascals. So that's P at 0. That's P at y prime equal to 0. How does the pressure change with y prime? Well, the pressure as a function of y prime will be equal to P at y prime equal to 0, and it's going to decrease as y prime increases, so minus, and the distance under the water is decreasing with increasing y prime, so rho times g times y prime sine 30 degrees, right? It's increasing, but only partially because it's on an angle. So the pressure will start at this value and it will go down, and we'll wind up with 8953 minus 998 times 9.81 is 9790 times the sine of 30 degrees is 0.5, so divide by 2 and we get 4895 y prime. Let's check that out. When y prime gets to be 1.829, we should be back to a pressure of 0. So 4895 times 1.829 negative plus 8953. Well, I get a fraction of a Pascal, which is probably just my round-off error. So, yep, that checks out. So when we go to do the force, we're looking at the integral from 0 to 1.219. Py is 8953 minus 4895 y prime times the w of y prime, the width, 2x prime, or 0.5521 times the square root of y prime, all dy prime. Again, that'll be integral 0 to 1.219, and we need to multiply these through, so that'll be 8953 times 0.5521 is 4943, and that'll be times y prime square root, so raised to the 1/2 power, minus 4895 times 0.5521, 2703, times y prime raised to the 3/2 dy prime. Or doing the integration, that'll go up to being y prime to the 3/2, and it'll have to be multiplied by 2/3, 4943 times y prime. Minus, this will go up to being 5/2, and it'll have to be multiplied by 2/5 times 2703 y prime to the 5/2, all evaluated at 0 and 1.219. So if we plug all of that in together, the 0 part will have no contribution, so we'll have to look at 1.219. 1.219 raised to the 5/2, so that's 2.5. Times 2703 times 2 divided by 5. That gives me 1774. Negative here. And this one over here, y prime to the 3/2, 1.219 raised to the 1.5 times 4943 times 2 divided by 3 gives me 4435 minus 1774 gives me 2661. Newtons, because we've worked the whole thing in meters, seconds, and kilograms. So that's the force that I get acting this way on the gate overall because of the integration over the whole gate. Now let's check and make sure that makes sense. This thing's a little more than a meter in this direction and a little more than half a meter in that direction. So it's around 1/2 a square meter. And it's at its deepest, it's less than a meter underwater, so shallower, it's probably half a meter underwater on average. So the force would be the pressure times the area, so rho g h would be 9.81, and we said that it was about half a meter underwater. And what do I get there? 998 times 9.81 times 0.5 times 0.5. I get about 2,400. $24.50. So I've done a check there. That's just a rough guess calculation, and it matches up really well with what I got when I did the integration. So I'm pleased with that.